Hi everyone. Thank you for coming so early to talk about a very complex topic. I hope that by the end of this talk you will understand a bit more what quantum technology entails and where we are at right now. We're going to focus mainly on cryptography and security because this is, well, the main topic of research currently for quantum technology, even though there are many other ways to exploit such a computer. So, quick word about me. So I work at a coding game, which has anybody ever heard of coding game? One person, great. Well, come here, you can explain. No, well, so I'm a competitive programmer. Coding Game is a company, we have a website like this where basically you program AIs that can play against other players' AIs. It's great to learn programming, to get better at algorithms as well. We also have some sort of screening product where you send a test to your candidates. So we pre-assess them before you take them in an interview and waste time for bad candidates. We can do that for you by sending you a very detailed report about your candidate. All right, that was the 2 slides about my company. Now we can get started with the real stuff. So let me get started with that. Quantum is the blockchain for nerds. So by that I mean it's a buzzword that's used in a lot of startups, in a lot of projects. Most of them are, don't really have a future, but there's still a lot of actors, big actors that are interested in that technology, and you will understand why. So, IBM has a really strong positioning on that. They are building actually quantum computers and toolkits. The Qiskit toolkit is a programming language that you can develop quantum algorithms on. It's very complete, so they are really investing into that technology. Microsoft as well. There's a quantum technology Nobel Prize given to a French guy in 4 years ago, I think. So it's really a very important area of technology. Google, countries, the EU as well. Those are maybe that flag stings a bit. I'm French, so a lot of various actors. So today I want to show you a bit what's quantum computing, where we are at today, talking about breaking cryptography as well, defending against people who want to break cryptography, and there's also ways to improve our current security using quantum technology as well. So, why do we need quantum technology? First, you may be familiar with Moore's law, which states basically, it was defined in 65 by a guy called Gordon Moore, who noticed that chips, the number of transistors in the average chip doubles every 18 months. So that's an exponential growth. Well, here, it's the axis is logarithmic, so you can see it's very linear. It's the number of transistors per unit of area. So we need to make smaller and smaller transistors and smaller circuits engraved in the silicon. Now we are trying to have a few problems with something called quantum tunneling effect. So this in gray is a perfect insulator. So you cannot have electric current pass through it. It's in theory, you can have perfect insulators in real life. Usually you will never see current, but actually electrons, if the barrier is small enough, less than a few nanometers, actually the electron can sometimes pass through it, even though it's a perfect insulator, because there's something called the uncertainty principle regarding the position of the particle, which means that it can traverse an impenetrable wall. And this is a problem, because in CPUs, you expect your electrons to be where they're supposed to be, not to jump from one part to another. So the issue is that we cannot keep making smaller and smaller chips. Anyway, we are reaching the size where transistors are just a few atoms wide. So anyway, we're going to have issues with keeping that exponential growth in computing power. So Moore's law is pretty much expected to start flattening out in a few years, so maybe in 5-10 years. So how do we prevent this? How do we keep going? How do we keep having this exponential growth? Well, we could find a solution to manage this tunneling noise, so the electrons that are going to jump from one wire to another in the CPU. We could make also try to work on more complex chips, such as 3D technology. So currently, the CPUs in silicon, they are not on a single layer. There's like the thickest one have 100 layers. But yeah, we could make much more to have like maybe cubic CPUs, stuff like that, to increase the density while keeping the large transistors that do not have tunneling effects. And otherwise, well, we could completely change our vision and try to use another technology which could keep this computing growth going. Tunneling noise, well, we are working on it. Well, I say we. Other people are working on it. It's still a very complex matter, but you can like correct the errors, make redundancy as well. But that's hard. More complex chips, so like 3D technology, too expensive for now compared to just like having multiple chips. And well, using another technology here, there are initiatives, and there's a big idea which is called quantum computing, which could be helpful to keep Moore's law kind of valid, have this computing power keep growing, even with this tunneling noise threatening us. So yeah, basically we are, the main issue is quantum effects, and the main candidate for getting rid of that would be quantum. So yeah, that's currently where we're at. We're working with very small technology, so we have those issues. So what's the difference? Maybe you've heard of that, like a bit is a 0 or a 1. A qubit or quantum bit is both at once. It's kind of weird, like if you haven't worked with quantum computing, you don't really know what that means, like what computations you can do. But that's actually what it is. It's particles. So qubits are mostly particles that have, until we observe them, so you know Schrödinger's cat, until we observe that, it's at the same time alive and dead. That's pretty much the same thing, but here we have some sort of a probability state. So the 0, for example, has 20% chance of happening. The 1 has an 80% chance. And that's pretty much all about it. But we can do computations with that. We can make them work together by intrication. So we can actually have very powerful computers. So when we measure, so here that little point is the state of the qubit. So it's not really like 20% 0, 80% 1. Those are complex numbers, but pretty much the same. And then when we measure it, so when we want to get its value, it's not going to tell us, oh, I'm 20% 0, 80% 1. It's going to collapse. So according to this probability state, it's going to collapse to one of those two possible states. So a 0 here in red or a 1 in blue. It's the superposition effect is going to get destroyed. So yeah, well, having two values at the same time, yeah, it's great, but it's only 2 times speed up, right? We can compute two things at the same time, but that's about it. Well, actually, we have an effect called quantum intrication, which means that you can like take several qubits, link them together to form a vector, and their state is linked. So we can, instead of having, for example, with 3 qubits, for example, we don't have like 2 states, and 2 states separately. We actually have 8 states. 3 bits make 8 states, and we can work with that. So with n qubits, we actually have 2 to the power of n different possible values that this vector can take at the same time. So, for example, yeah, the speed up is exponential. So when you take 100 qubits, you have, well, pretty much that much of a speed up. It's we cannot really use today's classical, so we say classical as opposed to quantum. We cannot use classical algorithms on that, so I'll get to that later. But it's still a very nice performance increase. So yeah, what you can remember is that for that part, we have 2 to the power n simultaneous states, and we can only make a single measure, which means that once you measure the state, it's going to be 100% towards the state you measured. It's going to destroy all this superposition and all the probability. It's going to collapse to one single state. The current issues we have is that qubits are very fragile, so they tend to evaporate, to unlink themselves. They have a lot of noise as well, so that's one issue we are trying to overcome. Conceiving algorithms on a quantum CPU is very hard as well. I'll get to that later. Also connecting qubits, so you may have like 1,000 qubits in your quantum computer. Actually, it's very hard, even with that, to link them together, to intricate them to make a 1,000 qubit vector. Yeah, so mentioning qubits are fragile, you may recognize this thing, which is the IBM quantum computer prototype. They love to demonstrate at exhibitions and stuff like that, so you may have seen one in real life. This whole thing is just a fridge. The chip is in there, it's super cold, but all the rest is basically a huge fridge. So this is the graph of usefulness of a quantum chip. So here we have the error rate. So I was mentioning on the vertical axis that, well, qubits are noisy. They tend to have errors in there intrinsically. We could make like a 0 error chip, but we are not there yet. The number of qubits is very important as well. Well, because if you have too few qubits, that's not a performance increase sufficient to go for anything that a classical computer couldn't do. So that's the purple part on the top left. But then as we keep going, so this red arrow is the expected progression of evolutions of the quantum technology. The useful zone is this one. Today we are pretty much at that point, this frontier, which is called quantum supremacy, which means that we have computations, we have problems that we are able to solve on the current small quantum computers that we have, that a classical computer couldn't solve. So there are a few very selected problems for which quantum computers are good. Currently, we don't have very powerful quantum chips, but well, that may be coming in the upcoming years. We don't really know if it's going to happen, if it's going to go way beyond that point, but we are hoping to get the first realistic machines in basically a decade, depending on who you ask. Some people say never, some people say next year, but the average is around in a decade. So we still have some time to prepare. Now let's get into security. So cryptography. We have two algorithms that can be used. Well, that have been designed and discovered that can work on quantum computers and are very powerful to break cryptography. Shor's algorithm. So you may recognize this. So it's a problem of factorization, which means given those two numbers, so they are very easy to multiply. You can just like take your calculator or do it by hand. Whatever the size of those numbers, your computer is never going to have trouble multiplying that. But in the other direction, given this n, it's very hard to find the factors, so it's called factoring. If I give you this number, unless you try a lot of possibilities, you won't really find a way to find those two numbers back. And so this is a fundamental problem that is used to make a lot of cryptography. RSA, notably, is built on that. So the private key is those two numbers. The public key is this number. And with that, you can have secure communications with private and public keys. So it's called asymmetric cryptography. This guy, Peter Shor, in 1994, I wasn't even born, but this guy apparently, out of his mind, because we didn't have quantum computers at that time, he designed an algorithm that could be used to factor very large numbers very fast. So let's explain a bit what Shor's attack is about. It was actually not built for factoring numbers, but someone found a way to use that algorithm to do that. So how do we find a divisor of n? So how do we find p, for example? Yeah, this calculator means it's about to get a bit mathy, a bit spicy. So as long as this is on, you can just unplug your brain for 2 minutes. It's all right. You won't need all that information next. So what do? We are going to pick a random number called a, which is smaller than n. We just pick it at random. Then if we do this, so there are many ways to find a divisor, but this is one of them. If we find a number p, such as this property is valid, so a to the power p modulo n equals 1, if we find this value, whatever is the value of n and the value of a, we're going to have around a 36% chance of having one of those two numbers being a factor. So even if those are none of those are a factor, we can just repeat the algorithm a few times. If we can find a way to find reliably such a p-value that works for a and n, we are going to have, after some time, we are going to find a factor. So maybe like I didn't compute the probabilities, but like if you repeat that maybe 10 times, you're going to have more than 99% here. So, well, this is the complex thing, because currently we don't have a way of finding a value of p in a fast way. What we do currently, well, we compute a to the power 1, a to the power 2, etc., until we reach 1. So this may take a very long time. Like p could be like in the order of like several hundreds of digits, so not feasible in computing, classical computing. But as you can see, this reaches 1, then 13, and then we go on. This loops around. So this is basically a loop. This is called the frequency of the number. And this is something we can compute extremely fast. using Shor's algorithm, using something called quantum FFT. And well, when you have this frequency measure, you just have to compute, well, the frequency is equal to P actually. You have to compute, well, the difference between 2P and P, it's just P. And so now with that algorithm, which I will not get into, you have found the p-value, and so you can go back to this and have a significant chance of finding a factor. Otherwise, you can just repeat that over and over. So now that we have this, well, we have basically solved the issue of factoring numbers. Well, it's not really an issue. Currently, it's more a protection because we are using that a lot in cryptography. And basically, all asymmetrical cryptography nowadays, all the things that use HTTPS, the signal protocol, all the stuff like that, they can be broken with this algorithm. So it's very worrying. So yeah, quantum supremacy means the death of RSA, Diffie-Hellman, L-gamma, all those systems based on a variant of this problem. So to do that feasibly with a quantum computer, we need to have, for n-bit primes, so currently the standard is 2048 bits. For RSA, for example, you need around n qubits if you have not too much noise. The state of the art, actually, with a 16-qubit computer, which is pretty much the biggest we have, this number, it's not even able to factor that. Not even 35. The biggest number we have ever factored on a quantum computer, actually, was 21. So as you can see, we are not there yet. But there's still a lot of research going on. So a lot of people now have a better vision. We can simulate smaller quantum computers to evaluate the performance of the algorithms, the feasibility as well. And so we have researchers, so recently, like last year, with 20 million noisy qubits, they can basically break RSA. So noisy qubits means like a quite high level of noise. I think it was like 1 in 1,000 bits in error. Can be broken in just a day. With 14,000 qubits, now we can factor the same size of key in half a year. So we are still finding algorithms which can be just put to use once someone gets their hands on a quantum computer. Now let's talk about another algorithm, which is called Grover's attack. Well, I won't get much into the detail inside there, but it's super interesting. It would take me the whole hour if I wanted to go in detail with that, but you can read articles on that. It's very interesting how it works. It's a very versatile algorithm that's used for any kind of search. It was used, I think, at the beginning for a database search, but people realized that we can use that for pretty much anything, and it speeds computations up a lot. So what we have is we have a black box. So this is not really a black box, but this means any function that we can implement with logic gates, so which means any function that can run on a classical CPU, on a silicon CPU, with an n-bit input, so any input, and the output is just a Boolean. Here, what we want to do is find any input that matches and that says yes at the end. So, well, this works, well, this algorithm is useful mostly if the yes is very rare. That's like for just a single input out of the whole thing. And we don't need to know what's inside that box. Well, we need to implement that, but the algorithm works for any black box that you want. So this can very well be used for brute force search, because that's basically what we want to have, like one input that returns us a valid value. And in terms of performance, we are going to reduce the search space, so all the values that we are going to try, from if, say, we have k values to try, if we want to try them all, the search for Grover's attack is going to be root of k. So it's not that much of a speed up compared to Shor's algorithm, but its power is that it can be used in basically any black box. So for example, we have two black boxes that we can re-implement to brute force AES keys, for example. So does this key compared to, does this key combined to the given ciphertext give a valid plaintext? So basically what we have here is brute forcing the AES key for a given ciphertext. What we have also here is hash cracking. So this is called pre-image attack, finding the input value that gave a given output. So including all proof of work cryptocurrencies, because that's something people are really worried about as well. All this can be sped up by a lot with Grover's attack as well. But for cryptography, it's not that powerful actually. So for n-bit spaces, so for example AES 128, it's basically reduced to AES 64. We divide by 2 the number of bits by taking the square root of the search space. So to keep the same level of security with that attack, so with that very generic attack, maybe there's other attacks that are going to come that target specifically some cryptosystems, but with Grover, we only need to double the key size. So that's not such a big deal, but like legacy systems will need to be updated. Systems with fixed key sizes or search space sizes, such as SHA-1, AES 128, will die. But yeah, that's just going to be a minor inconvenience compared to Shor's attack, which will completely kill RSA, for example. Just a quick side step about quantum programming. I have done a few competitions in quantum programming. They are very hard. The algorithms are extremely hard to design. And there are many reasons. One of the main ones is that it doesn't look anything like what we've seen in any language, like with if, else, for loops, stuff like that. You basically program with logic gates. And those logic gates, they have very precise conditions, and well, you have to find ways for all these superposed states to work very well together and give you a meaningful result at the end. What I mean by meaningful results is, oh yes, I forgot about that. Yes, well, that's pretty much what I said. So the meaningful result is that because you have a huge superposition of so many states, and you only measure one of those states, you need to make the end result have meaning, because in any classical algorithm, you input something, the output value is exactly what you need. In quantum, it's going to do like mash all those values together, all those computing. You have so many output values, but only one of them is going to be returned. So what you need to have is an algorithm that is reliable. So first, here's the end state. So we have 3 qubits that are intricated in this algorithm. Let's just say that's the output state. We are going to measure it. We can only measure the output once, because otherwise it's going to give us the same value every time, so it's not really meaningful. So here, for example, I have a 24% chance of measuring a 0, 0, 0, assuming some input value. 2% chance of measuring a 0, 0, 1, etc. So if I run this algorithm, I measure it. It may tell me like, yeah, that's a 1, 1, 0, the result, with an 18% chance. I run the exact same algorithm with the exact same conditions. Quantum technology makes it so that, well, it may return like me 0, 0, 0, etc. So if I want to have a meaningful result, maybe I want to measure that probability space. So I need to run that a lot of times to get an idea of what shape it looks like. Here we only have 8 possible values at the end, so we don't really care, but remember, like what I said with 100 qubits, the number of possible states was from here to there, with like the 30 digits. So that would not work. So what we need to have is very spiky output, like one value that really stands out from the rest, which is going to be measured pretty much all the time. And this is going to be the meaningful result that we need. And designing algorithms such as this is the case, and that, of course, the output depends on the input and actually give us some information and some computing value. It's extremely hard. So yeah, we basically need to put all of the other states to a probability very close to 0. And in that case, we only need to run the algorithm a few times to double check that this is actually 101 that's spiky. So yeah, here's the symmetry of all the things in cryptography that are going to die. You may recognize some of the names. There's going to be many more that are going to get killed. So this is going to revolutionize the state of secure communications. Are we supposed to panic right now? I want to say kind of yes. Let me tell you why. Let's assume you are communicating with someone on an encrypted channel. So this is encrypted data. Today, so I send a message to anyone. Today, there are no quantum adversaries. Or we suppose that because the first person to get a quantum computer is likely not to tell the world. But my communication today, I send that today, it's secure. Nobody can break it. Even if someone intercepts that, fine. It's just random garbage, right? Yeah, well, they can store it on their disk. Wait a few years. Quantum supremacy, quantum computers. Now we can decrypt that with quantum chip. And we can decrypt the communications that were made today, actually. So maybe in 10 years, today's communications will be all decrypted. Well, nobody has the reasons and the budget to do that stuff on an extremely massive scale, right? So that you and me could be affected, right? Well, but I have good news. There are ways to secure our communications today, or today they are not quite extremely ready, but we have ways of securing communications that run on any device, my phone, my computer. I don't have quantum CPUs, by the way. So they run on classical silicon, but they are not broken by the algorithms I've shown you earlier. So this is good news because we have ways of having still secure communications with poor stuff, poor hardware, and defend against the very rich. There was an experiment conducted by Cloudflare and Google a few years ago. They put a layer on top of the existing HTTPS, of course. There was an additional layer that they tried to implement that kind of algorithm, which is called post-quantum cryptography. It was a bit slower, the exchanges were a bit longer, but the experiment worked. So actually we have those systems in place. They are not widespread right now, but a lot of people are working on that. So we have the Open Quantum Safe, for example, which is basically a fork of OpenSSL with post-quantum cryptography built into it. AWS, you have the ability to store your post-quantum keys, for example, in the key stores. Password managers such as Dashlane are trying to implement that as well. By the way, those cryptosystems are extremely hard to implement. Like even to understand how they work. It's like research papers of 20 pages, full of mathematical notation, so nothing even remotely close to what we have currently, which you can implement in a few lines of Python. NIST as well, very important thing. So the US National Institute of Standards and Technology, they are conducting contests for designing post-quantum cryptography. Researchers are submitting their algorithms, and so they are currently in the way of selecting. I think there were 15 finalists, then currently we have 7. So we are selecting a few candidates that are likely to be used tomorrow. Well, one of those 7 finalists was actually kind of excluded because someone found a way to break them on a classical CPU in just a single weekend. So we are not quite there yet, but we're working on that. So lastly, I want to talk about making cryptography with quantum effects. So here it's not going to be about quantum computing. It's going to be another quantum superposition effect that we can actually use to secure the channels. So basically, to design perfect cryptography, you need 4 things. You need your key entropy to be greater than your message entropy. That's something we can do. It's quite easy thing called one-time pad. Perfect key sharing scheme. So this means the way of having the same key on both sides. Currently, we do something called key exchange, which is based on Diffie-Hellman cryptosystems, which pretty much will be killed by Shor's algorithm. We also need authentication, which means you need to verify that the person you are talking to is actually who you're expecting. And you also need perfect implementations with perfect implementation, which means 0 bugs. So yeah, one-time pad, perfect sharing scheme is what we're gonna talk about right now. Authentication, I won't get into that, but it's super interesting, and well, perfect implementation. Everyone does that, right? So yeah, key exchange, currently it's based on Diffie-Hellman. It's in HTTPS, most of the time you have something called ECDH, which is based on elliptic curves, but it's the same algorithm, and it's broken by Shor. So we can actually use quantum superposition for secure communications. The setup is going to be this one. So I'm going to talk about QKD, quantum key distribution, with an algorithm called BB84. We have 2 computers that we want to secure the communications between them. We also have the attacker who can intercept both channels. So well, this is the setup we always consider in cryptography, like your adversary has access to your channel and complete access to read that. But now we have 2 channels. So classical channel, anything you want, optical fiber, copper, Ethernet cables. The quantum channel is going to be light channel, so we are going to send packets of light. We actually need it to be light and not anything else, because we are going to use properties of photons. There are currently implementations of that. I don't think it's BB84, it's a variant, but it works pretty much the same. The Chinese actually have a satellite that they did experiments on, where they could send quantum information to secure their information. I think like it was more than 1,000 kilometers away, using 2 ground bases and a satellite in between. So how does BB84 work? We are going to have photons carrying 4 possible information. So the first information is the base. So it's the orientation of the polarization. I don't know if you remember high school physics, where you have like polarized light. Light can be polarized in any direction. So like it's the orientation of the wave. It travels in a straight line, but it can take pretty much any value. Here we are going to say either it travels so in the diagonal base, which is either in that direction or that one. or in the, so I call that the X base, and the plus base is going to be either vertical or horizontal direction. We also have a value which is going to determine which of those two orientations we take, and so we are going to end up with 4 possible states. Those 4 possible in orientations of the light are going to give us some very interesting things. Just a quick reminder, so, or a quick information sheet about quantum principles. There is something called the no-cloning theorem, which means that you cannot take an intricate state and just make a copy. That's just not possible to do that. To do that, you would need to measure the thing, destroy the superposition, and then, well, it's not really a copy anymore. And there's also one thing that you cannot find the base. So this thing, you cannot find it without guessing, without trying to guess what the sender wanted to send you. You cannot just like look at a photon and say, oh yeah, it's oriented in that direction. There's no way to do that. So let's say the sender, so we call them Alice and Bob, usually in cryptography. The sender is sending those information. So here is a 0 in the diagonal base. Here is a 1 in the vertical base. So we are going to send many photons. We send only single or very small groups of photons. If the person at the other end of the channel is using the correct basis, so here the X base was used to send, it's used to receive as well. If that's the case, so the measure base is basically you put a filter which has either that direction or that direction. You pass the photon through and you measure it with the screen at the other end. If the photon passes through, you can actually view it. Otherwise, it gets filtered. So, for example, if they have perpendicular values, the photon is not going to pass. So you can measure the original value with that. So after the filter, we can reconstitute the exact same value, and we can actually extract this information by looking at the screen. If we get the basis wrong, so here for all 6 bits we are using the wrong base. We are using the, well, for the diagonal ones we are going to use the plus filter, and for the vertical ones we are going to use the X filter. Here the photon will be forced to take one of those 2 values with a 50-50 chance. Because if we take light that is oriented that way, pass it through a vertical filter, it's basically gonna divide by half the brightness of the light, and that's exactly what we are doing here. And so here we cannot guess the base that was sent, and so the value is going to be coerced to either the vertical one or the horizontal one. And the bit you get at the end is going to be random. You get a 50% chance of getting it correct. So if you have someone intercepting that channel, so here Alice and Bob are using the same base, so Alice and Bob are getting the same information on both sides. If Eve is getting the base wrong and they are unlucky, Alice and Bob, even though they are using the same basis, they are going to have different information. And so there are actually ways to check that you have the same value on both ends and detect if someone is listening. So BB84, it's not immune to interception. Each side sends a subset of what they received. And if any of those verification bits are incorrect, it means that someone is listening to the communication and has actually modified the information by observing it. The basis and the data, by design, they have to be random. You cannot use that to transmit any information, otherwise you lose on security. So you cannot send a message directly through this quantum channel, but you can use those bits to make a shared key. And those and then you can send all the information that's left on the classical channel. So, to conclude, just a few key takeaways on quantum technology. So we have many unknowns about its future. We don't even know whether or not we are going to have a quantum computer anytime. I think personally it's going to come in the next decade. We are going to actually see governments and large companies having those kind of computers, but there are unknowns, and we are not immune to having it completely fail, and you have wasted 50 minutes of your time today. But yeah, it's likely to be the next huge tech cycle, like after the web, after mobile. Quantum is likely to be the next big thing in tech. It will change the face of cryptography if it comes. There's no doubt about it, and you may not hear of it as a user, but as an engineer, you will suffer from that. And lastly, we should consider quantum as an ally. Well, we've seen it can help us achieve more secure communications, but actually there are so many more things it can do. We are currently looking at the security implications, because that's why so many people are putting money into that, because, well, governments have the money and governments are interested mostly in security currently. But we have like quantum machine learning, we have quantum computing in general to do so many things. There are so many applications, high performance computing, very efficient storage, things like that. We have a lot of things to do and to explore with quantum computers. Thank you. We have 3 minutes for questions, and I'll be around after if you're too scared or don't have time to ask the questions. Thank you.